Thank you.
Thank you. Yeah, I'm sorry about this. Forgot to record. Anyway, this was a discussion of parametricity, really. And in Haskell, if you have functions like this and they are automatically parametric in type parameters, and so then they satisfy naturality laws. And with naturality laws, this is true, that this type is equivalent to this type, but without naturality laws, it is not. So and this, now I also wanted to make a comment about this essence, right? So what is this essence? So there are many cases that I encountered in derivations in my book, where you have a function with a type parameter that is that satisfies some naturality law. And so naturality law with respect to A. And then there's another function that only has a second type parameter, and they are equivalent. So the types of these functions are equivalent. You can have an isomorphism, but only due to naturality law. So in other words, naturality law can get rid of one type parameter, and then you can simplify your function. So this is very similar to Yoneda.
So what do you mean naturality allows you to get rid of the parameter?
Means that the type, so this is kind of a type with a type parameter C. So if you wanted to define this function, you would use a type parameter C in its type signature. And this is equivalent to FA, which does not have the type parameter C. So using this equivalence, you have killed the type parameter C. So it's like
but
saying—
C was bound, so it sort of wasn't free anyway.
Well, that's not so, because it was bound outside.
Okay. You're saying that the inner function there would be, yeah.
So let me make this example like that.
Okay.
Right. So if you wanted to define this function, you would define it like this. You would have to put a type parameter outside. And so you would have a function with two type parameters here. And this is a function with one type parameter. So, well, because f doesn't have to be a function, but it doesn't matter. So it's a value with one type parameter. This is a value with two type parameters. And so the type of these values are equivalent, only given naturality law. And this equivalence is realized using functions that map from here to here and back. And these functions always look the same. To go from here to here, you insert identity function into somewhere, into one of these arguments. And to go from here to here, you add fmap with respect to C. So you always have this weird situation where you keep doing the same thing. You keep finding, and in Scala, one example of this is, let me see if I can find some other place to write, is flatten and flat map. So this is a standard definition. So you see the equivalence of these two is obtained in the same way. You put an identity function in here by putting a equal to f of b. And then here you have f of b going to f of b. So which is kind of this type signature with b instead of a. And if you want to go from here to here, then you take this function, you apply fmap to it, and then you apply flatten. So this kind of pattern repeats all the time, where you have functions with two type parameters that are equivalent to functions with one type parameter. And the equivalence is realized by inserting identity function in one of them and using fmap with another.
So in the case of the identity, I guess, in general, it's sort of unifying the two types. So B and or A becomes f of B. So,
Yeah.
it's, all of a sudden there's only one parameter because
Right.
you forced it.
Right. So yeah. So what I was going to say is that this this essence here is the Yoneda lemma, and so it tells you that Yoneda lemma was everywhere actually in all of these cases, all of these equivalences. There's a Yoneda lemma that you can just use. You don't have to prove every time that they're equivalent. Every time there will be a naturality law. Every time you will put in some identity function, and so on. Every time we'll be doing the same proof in a different case. And so this saves you all that proof. So you just prove it once and that's it. Here you introduce identity, you get f of a because a is equal to c. And to go back, you use fmap on this. So it's a very, very frequently used pattern. Like I have like 5 or 6 examples I can write down. Anyway, so that's.
Can you write Yoneda like in Scala so that it would apply to like flatten and flat map, or is it more like a macro?
You can, yeah, you can. You can have a function that takes a function of this type and returns a function of this type. There's no need to write macros.
But I mean, is that just by having one Yoneda function and you just somehow plug these things in?
You probably could, yes. What you would need to do is you would need to put type quantifiers in the right places. Because it's written like this, it's not obvious where the type quantifiers need to go. You need to have a function from like all a b and then a f of b and so on, from all this to all for all c f f c to f of c. Right, so it needs to be this quantifier inside into here. And once you realize that this is what you need, then it becomes easy to write. And then if you want to apply Yoneda to this, then you would have to, I'm not sure what you would have to do, but for example, you would have to say that this is a functor that I'm using. I'm not sure how you would do that in Scala, but certainly you can write ad hoc functions of this kind. I'm not sure if you can write once a Yoneda, which is so general that you can get this by specifying Yoneda. Maybe you can, but it will be a lot of boilerplate. Like you would have to define a type constructor for this, maybe for this another type constructor. I'm not sure. So yeah, but certainly you can write code that transforms a flat map into flatten and back. And then you can call this code with a specific implementation of flatten, and you get a specific implementation of flat map. So imagine that you had a type constructor that have several implementations of flatten. Then you can automatically derive the corresponding correct implementation of flat map. So anyway.
Which is basically monads, right? I mean, all monads.
Yes, but I'm saying that there could be many implementations of flatten for the same F.
Oh, okay.
So each of them could be mapped to its corresponding flat map automatically. So there are many monads where there's only one implementation of flatten, but there are some that have many.
Okay.
Can someone say a little bit about the following paragraph with the CPS transformation there? I think that means continuation passing style, which is a term I have seen, but I don't really know what it means.
Yeah, well, I would say the key to understanding is this line. So, sorry, this one.
Oh, okay, yeah.
Continuation passing representation of the type A is this. So, yeah, so the continuation passing style means that instead of values returned directly, you take a continuation that will consume that value. And you call that continuation maybe later. When you're so instead of writing a function that returns A, you write a function that takes an additional argument of type A to R and then returns R. So that function will compute A at some point, and it will call this on that A and get an R, and then it might return that R. Or it could actually call that function many times on different A's, if that's interesting, but that doesn't matter. So
it's sort of like, you know, if you have the B to A function and you're using it somewhere, well, then you're going to do something with that result and compute some R from the A that you got back. So this sort of flips it around and says, well, let's not do the function yet, but give me what you're going to do once you have the answer, and then I can feed it the A or feed it to B, and it will give me the right answer.
Right.
I don't know if that makes sense.
So B to A is equivalent to B to, for all R, AR to R. And for all R, we can pull out. And so this is like a function with two arguments. And so the CPS transformation consists of taking a function like this and replacing it with a function of this type. So this function has one more argument. So this first function had one argument B, and this function now has two arguments B and this continuation. So that is the idea. So like Peter said, continuation could represent some next steps that will be done with the result of this function. And so you gain some advantages in compiling if all your functions have this form. I forgot exactly what happens when, so if your programming language enforces that every function has this form, then you could compile that programming language in a special way. And so then you could, for example, do tail call optimizations much better or something like this. And of course, it's not convenient to write in this way, actual programs. So you write them in the usual way, but the compiler performs the transformation automatically. It replaces all functions by this kind of functions. And then things apparently become easier for the compiler. So yeah, and so then it just says that this transformation is actually a type equivalence. The initial type A is equivalent to this type because of the Yoneda lemma.
If I may add a little bit about continuation pattern semantics, it was originally introduced, created by Strachey and company in order to model non-local flow of control. So in order to do basically denotational semantics is a functional representation of a program. But if that program has something like go to A, where A is some label somewhere, then how do you model that using a function where composition of parts, the semantics of parts is composed to get the semantics of the whole. And so functional programming doesn't allow this kind of non-local flow of control. And so continuation is introduced to say, the rest of the computation from this point is represented by this function, and then the rest of the control from somewhere else is represented by another function. And then when you have a go-to, then you can say, you just go to this continuation, and then, that's one way of modeling it in a purely functional way. By having one level of indirection that says, to get the result of the rest of the computation, you apply this function to the input and so on. So that's the motivation for it. And this representation here, looks like that because you're abstracting, instead of values, you now have functions. So.
Yeah, I can imagine writing code where every function has this type. So then you have a function calls that always look like this: f of some x and then continuation.
Right.
Right, and then inside that function you have some other call with some other continuation. Right. And so inside that code, you are having another function with some other continuation. And so here you're free to, so suppose now here you have found some result, which is A.
Right.
Now, instead of returning it, you call one of the continuations on it, but you're free to call each one.
Exactly.
So you're free to call, for example, this continuation, and then you will jump out of all of that. You'll stop evaluating the rest of this stuff.
Exactly.
These continuations will never be called because you directly call this one. And so this is like a go-to.
Yep.
And so this is like a go-to where instead of labels, you have these continuation functions. It's very inconvenient to write, of course, in this way, but and it's quite unsafe to do a go-to.
Yes.
So
yes, I mean, Scheme has continue with current continuation, right? Call
Right.
with current continuation. And that's a very powerful construct that allows you basically to model any control structure you want, because
Right.
yeah.
Right. So you can model all kinds of things. You can model even concurrency.
Mhm.
But the result is, of course, the code becomes unreadable. Because here you have this K of A. And
Yep,
now you're supposed to remember what K was.
right.
And it's not K prime and it's not K double prime, right? So, and of course, you know very well what all they are, these things. So it's just like a go-to a label where you're supposed to know what that label is, what it does.
Right, right.
So, yeah, don't use this.
But the reason why it's used in as an intermediate step is that when you have the explicit case, then you can convert that into, sequence of instructions, right? Basically,
Yeah.
you can linearize the control flow by expanding what the individual keys are, because they basically go to this statement with that label and execute from then on. So yeah.
Right. So you just, yeah. So for compilers, this is an interesting technique.
Mm-hmm.
But most of us
It
don't need to do
corresponds
it.
more to go-tos in a sense.
Yeah, well, it's a functional, completely safe go-to.
Anything you
Still,
can do in an
yeah, you
imperative language, you can do
still
here.
jump to a label, and
Yep.
but you're guaranteed to have the correct type of
Mhm.
A and K. So you could not compile if this K did not take arguments of type A. So you cannot jump to the wrong label accidentally.
Mhm.
You can jump to a label where the types at least match.
Mhm.
But yeah, so if that's what you want, then you should do this.
But you're saying that most of us won't need to use this style most of the
No,
time.
no, no. I mean, this is more for implementers of domain-specific languages, and usually you have continuation-based APIs, and usually you want to convert them to some more strictly controlled APIs, where you're not able to call arbitrary continuations from arbitrary places. For example, in Scala, you would convert this to a future-based API, and futures are much easier to see. But, you would not use callbacks. I mean, continuations are like callbacks. You, instead of returning a value, you jump to some other piece of calculation which has been given to you as an argument. So it's a callback. So you call the callback, but you don't know what this callback will do. And you don't know if it will ever return, or if it returns, then what it will return. You don't know that. So
Yeah, that's a very good point. Callbacks are essentially continuations,
yes,
right? Basically,
yes,
you're saying, yeah, on this event, continue with this, some other event, continue with something else. And then that callback then contains other callbacks. And that's why we have this very, convoluted code in callback-oriented programming. But also for languages, most languages do not have go-tos anymore. But the last residue of that is things like try-catch blocks, right?
yeah,
When you have exceptions and then you want to escape out of that block to some enclosing block outside, then continuations are necessary to model that in a functional way. So
yeah, that's true.
But although
There are
continuations may not be part of our life most of the time, I mean, I work in TypeScript and JavaScript, and callbacks do show up. I mean, that is a
yes,
thing I expect to run into. So it's not that different, I guess.
Right.
Yeah, and then you have a very difficult life with that kind of code.
Exactly.
Well, if you're careful, is it really that bad?
Right. Well, yeah.
I mean, you got to be, yeah. I mean, I guess it depends. It depends, yeah.
All right. So, shall we?
So
Are there
just going
any?
back to the existential part here, it's, you know, in languages, right at the top of the screen there where it says for all R exists A, that sort of stuff. I mean, it's interesting that in, you know, a dependently typed language, this stuff doesn't look as weird because, you know, what you're really in some sense saying is that there's like for all R, there's A cross F of A cross A to R. You know, it's just that but it just happens that that A is dependent on the other parameters. So in languages like Haskell or mathematics, you write it separately, but
Yeah.
in
Yeah.
some sense, in a dependent language, that's just for all R a triple to something, where the first parameter of the triple is a type.
Yeah, but but this is because, isn't this because this existential is under a function?
It's on the
Well, it's out-
domain of that arrow, right? The outer arrow. We're pushing the universal that is over the A, I mean the left-hand side arrow GR. And now we're putting it into the contravariant part of the arrow constructor, right? And that's why we have to flip it to existential, it seems.
Right.
Right. That's
Because
it.
the domain of that function
Yes.
has A, but the range doesn't, right? So
Right.
you basically, if you have something that's like that form, then it becomes an existential.
Right.
But it actually just kind of looks like you're undoing some currying if you look at it in a dependent type, because that for all A is just another function from a type, arrow, F of A, you know,
Yes,
so
yes,
it
yes.
just ends up being another sort of example of uncurrying or whatever.
Mm,
Right.
yeah.
That's right. Yes, correct. Yeah, so in some sense, you don't always need to write this existential because you can just write a type variable as a value.
Right.
Yeah.
And that's essentially what existentials are in dependent types. They're basically these dependent tuples, dependent pairs.
Yeah, well, it's interesting that you say that this is a lot less weird to write it like this. But to me, it's more weird. Because then it's not emphasized that this A plays a completely different role from this and this.
Right. You really want to write it more like, you know, that A is more like A colon type, because that first parameter is really type, not A.
That's right. That's right.
So, you know, but it's bound. So you really want to say something more like paren A colon type, and then the rest of that.
Yeah, well, that's right. Yeah.
Yeah. So it's really a triple containing a type, a value, and a function, where the value and function both depend on the type.
Okay.
Anyway.
Yeah, well, it's an interesting
Just when I was working it through, it's like, yeah, you didn't need that much because you could just sort of swap your arguments around. And
Yes.
wasn't as weird.
Yes, that's true. Well, what I do is I just always think that a universal quantifier is an infinite product of all types, and an existential quantifier is an infinite coproduct of all types. And so here I have a coproduct with respect to all possible A's. And this coproduct is an argument, or is in the domain of this function. And so then I can equivalently represent that coproduct in the domain as a product of domains, product of these domains.
Going back the other way.
Yeah, so then it's the same. The product of these is equivalent to a big coproduct in the domain. And so that is clear, and that is you know, that kind of avoids mistakes, because there you can make a mistake very easily in here if you don't see that this bracket stops here. It won't be true anymore. And so you have to kind of make sure that you don't make a mistake rewriting this quantifier in the wrong place.
Right.
So anyway, for me, this has become kind of clear. So do we have other questions on this, or should we go somewhere else?
I think, I don't know if we get to it, I'm curious about that in the representable functors section about the Napierian, or however you say that. Yeah, right there. I guess I was confused because positions is, so f is a functor, so it takes types to type. Log of f is a type, right? So f log of f is a type. That makes sense. But then positions being sort of plural almost suggests that that's a type, but it isn't. It's a particular value in that, of that type. So why is it?
Well, it's just tabulate plural. Is a particular, well, tabulate is a particular value of this type, right?
Okay.
And positions is a particular value of this type. And by Yoneda, these types are equivalent.
Isn't it look up and tabulate types? Oh no. Well, those
these are inverses. These are inverses.
Okay, got it. I see.
But these are equivalent types. And so if you have a value of this type, that gives you a value of that type automatically, and vice versa.
Oh, that's where you need it. Okay.
Right. So this is a specific value. So imagine that f is an array of 3. Then log f is the type 3. So fa is a. Log f is 3, which is 1 plus 1 plus 1. Right, so three unit types with a coproduct between them. So what is then f log f? It is f3, which is 3 times 3 times 3. So then you need to give a specific value.
Oh, I see. Like
Right. So for example,
201 or something.
yeah, maybe. So these are positions.
Mm-hmm.
And it gives you as many positions as values inside F. And so each value should tell you what position that is. So what is the index of that value? And for example, you could say, so in other words, it should tell you, for example, what is this? Is this corresponding to this first one or to the second one or to the third one here? Because this corresponds to one of these. And this also corresponds to one of these. And so the positions should be something like this one is 1 plus 0 plus 0 here. And this one is 0 plus 1 plus 0. So, and this one here is 0 plus 0 plus 1. And so then you would have some reasonable map of positions, but you could have a different map of positions. But in any case, that's when you want to tabulate. Tabulate means that you give me, for each position, you give me some value, and then I know how to create this. And you could do just by mapping on positions. That would replace each position index by the value that you're given. So anyway, this is, to me, this is a mystery why you need this. Maybe the only thing you really want is this lookup. So you want to kind of index your data. So this F contains a bunch of values and you want to index them. So you want to kind of say, my value is at a particular index. Index is a value of this type. So
two questions. If instead of A cross A cross A, it was A plus A plus A, I take it wouldn't be Napierian. Is that right?
it wouldn't be, no.
Okay. And then they talk about the example pair. Is that, I wasn't sure. I mean, is that kind of like your F of A except with 2 A's?
Correct.
Or what, okay. Because
Right.
to me, pair generally takes 2 types.
No. It's pair. It's a pair which is all of the same type.
Yeah, that's not the one I would think of, but okay.
Yeah. So yeah, you only have one type parameter here. So you have FA.
Right.
This is fun. This is kind of very interesting. So f of a is a to the power 3, right? And so the log of something
That's
to
where
the
that
power
came from.
3.
Correct.
Yeah, we're
Yes,
taking the exponent as a type 3, which is the sum of 1 plus 1 plus 1, where 1, of course, is the type that has, what, a singleton element?
Yeah, it's a unit type.
Yeah.
I'm just trying to rearrange this.
Right. So this is only going to work with sort of basically product-ish functors. Right.
Because there's no, if you have FA, what you said, Jung Il, like A plus A, right?
Right.
There's no way to tell me in which part of the disjunction I'm
Right.
supposed to have my value.
Right.
So this positions will tell me that there's only one, but it will not tell me which part I'm in. And so that is not Napierian.
Okay.
Yeah. Oh,
Yeah, and so it's a weird thing, yes, but yeah, it could be useful for types that have specific shape,
mhm,
where you have a type that kind of measures the length of your data set. And I mean, you could have other things in this data set, actually. But actually, wait, no, I don't think you. No, wait, it's others. No, you cannot have any other type of stuff. Like you cannot have a constant type,
no.
like FA equals C. You cannot have this
Why not?
because values of type C are not described by this. And you're supposed to have an isomorphism between FA and this.
Right.
So your FA must be of this type. It must
Right.
be some function from log F to A. So, and this is not in the form of a function from anything to A. And this is also not in the form of a function from anything to A.
So are we saying then that F has to be some A to the N for any
Well,
N? Is that the only
N
F?
doesn't have to be finite.
Right. It doesn't have, well, if it's not finite, then what is log of F?
It's going to be some type with infinitely many possible values, like integer, for example.
I see.
Or nat, maybe, or something.
Nat,
I
yeah.
see. So
You
it
could
would
have
be
nat.
existential N dot N.
But
Or
also maybe you,
existential N dot one, basically.
Not sure what you're talking about. Why more existential?
Okay, I'm trying to figure out if F is A to the N, where N is infinite, then log of F would be an infinite sum, right? 1 plus 1 plus 1
Yes.
dot dot dot.
could F
And-
of A be list of A? That sort of has an infinite potentially.
No,
Well,
list
each
is
one
a
is
list.
finite,
No.
but
List is a disjunctive type.
Right.
It
This
is not
would be
Napierian.
yeah.
It is
A
not
plus A squared plus A cubed and so on. So,
All right.
so.
All right.
okay, I see. It could be infinite or unbounded, let's say. Okay.
So positions.
Right.
It is nat to nat.
Mm-hmm.
No problem, right?
Mm-hmm.
So you could define what that is. For example, you could define positions as identity function. And then you would have a natural way of parameterizing an infinite list of values of type A.
Right.
Okay. Yeah,
So
I
as
mean,
your example,
nat
Go ahead.
arrow A is effectively the same as A to the power N, where N is
Yeah.
infinite, right? So
Yes. Yes.
Okay.
Yes.
yeah. Mhm.
Just as
so
a
your
historical
F
note,
of A doesn't have to be just A cross A cross A. It could have
No.
something like,
No.
3, the type 3 that you wrote before, arrow A as one of the components and things like that. So I guess you can get a
Okay.
little more structure.
You
I
could.
see.
You could have things like P, Q are going to A.
Mhm.
Then you have some extra structure in P, Q, and R. So your log F is PQR. So it's
Yeah.
not just, it's some kind of extra stuff. Right. Anyway, Vlad, I think, wanted to say something. No,
Oh, no, I was just saying,
no,
this,
not Vlad.
I was
Sorry.
wondering if this was
Hugh.
related to the 16th century mathematician Napier, who kind of invented logarithms. And yeah, but that's,
Yes,
that's what it's named after, apparently.
it does have that formal resemblance, that log of something to the power. Yeah.
Yeah. Anyway, just a historical note.
That's true.
Interesting. Yeah.
Yes, obviously that's true, but I don't understand why they spell Naparian like this.
Yeah, I don't know, but at first I thought no, it couldn't be him because but it's got logs in it and it's got
Yep,
that.
it's got
Yeah,
logs.
it's just a variant. Yeah.
It's got
Spelling
logs.
was
Yeah,
more flexible back then.
they left out the I.
Yes.
Too
I
hard to
wonder if that-
pronounce.
wonder if that has something to do with the Latin spelling.
Ah,
Could be.
The Latin spelling of Napier.
Right. How would you Latinize Napier?
Well, there's also that, spelling even in English wasn't very standard back then.
Was he French?
He was a Scot.
Latin
Oh.
word for a napkin or cloth.
Anyway.
side note.
Yes, that's
Yeah.
Hmm.
Oh my God. See this?
Spell.
Nepero. John Napier.
Hmm.
Ioanne Nepero.
That's
Doesn't
it.
mean-
Napero. See, the I disappears.
Yes.
Well,
Anyway, that's
we can
why.
ask the authors of this paper or the original developer why they did call it.
Yeah, you can just look at the Git history and find where it was changed.
Well, one of the authors of that paper that they're referring to is the author of this paper, right? So
Yes.
I assume it's the same Gibbons.
Yes. So anyway, let's spell correctly.
So do we all by now have some intuition as to the structure of instances of the Yoneda lemma? And I'm just reading the last paragraph before profunctor optics. Are we there? I'm sort of partially there. I'm still don't have it like in my back pocket yet, where I can just pull it out and apply it, but yeah, getting there.
Yeah, well, I would suggest doing exercises with types like this. What is this? Every time, what you need to do is you need to rewrite this type using currying or other things into the form of a Yoneda lemma, which is for all C, A to C, FA, with some F and some A, maybe not necessarily the same. Let me call this X. And then you would have immediately a simplification
Mm.
So, for example, for this, you say this is FC, so F is identity functor, and this is a unit type. So it's a unit to the C, which is equivalent to C, and this is unit because X is void, X is 0.
Mm.
And so the result is F of 0. And so this is identity functor of 0, which is 0. So this is 0.
That's an empty type?
Yep.
It has to be true for all C, including the empty type.
Right. Correct. But you don't have to find some ad hoc proof. You don't have to try to understand why this is true.
You just plug it in.
Yep.
So we're using the empty type as sort of the representation of false.
Yep.
Because for all C, C is false. So, okay. Interesting.
Yep. So similarly, you could simplify those other things. Now here you would need the contravariant version of Yoneda. Perhaps, not sure, actually, maybe not. Maybe you won't, but it doesn't matter. So, because you could say here, for example, you could say F is a constant functor that gives you A always. And this is a unit to C. And so this is F of unit, but F is a constant functor that gives you A always. And so this is A.
But it does also have the feeling of existential, because you could rewrite that as parenthesis exists C, C,
Yeah.
parallel A.
Right.
Right. Again, universal going inside the domain of the function constructor.
Yes.
Yeah.
Yes.
Okay. I'm
Yeah.
beginning to see a pattern here.
And then, but you cannot do this with other examples. So this is only for this example that you can do this, and then you can say, well, this could be a unit type here. And in any case, I don't know what that is, so I won't be able to use it. So this is just A.
Right. You won't be able to use it, so all you got is A. Right.
Yeah. And so, but you don't have to have an ad hoc proof. Well, you can just apply the Yoneda.
By massaging your type appropriately. Yeah.
Right. And that's what you do always. You have to massage it into this form. And if you cannot massage it into this form, then Yoneda is powerless and you cannot simplify.
So that last example, I think last time when I was asking about an example of an interesting type with a universal quantifier, someone mentioned, we didn't give a name to it, but it was like serialize, right? For all A goes to string.
Yeah. I think I asked that.
No,
What type that would be.
That's this. For all C goes to A. Yeah. Now, the thing is, this is supposed to be a natural transformation, fully parametric. Serializers cannot be fully parametric.
Right.
They work with specific types. For each type, they do different things. So serializers are not covered by this, and they are not equivalent to this.
So, but if a serializer type were to be natural, then it would be trivial. It would be the same.
Yes, yes, yes. Which basically tells you that serializers must be non-natural, if non-parametric, if you want them to be useful.
Right. Okay.
You can make them parametric by adding in an extra parameter at the beginning, which is like essentially the type class for serializing that thing.
Yes,
Right.
which
So
itself will not be fully parametric either.
right, but you're passing it in, so your function
passing it in.
itself is
Yep.
parametric, but yeah.
Yep.
You just basically, when you call it, you have to say, okay, here's basically the schema that describes my data, and then it can
Right.
work parametrically.
Right. Yes. Yes. But the function here as written cannot.
Right.
Right. Anyway, so you can just go through these kind of in the same way, and then you'll see that this works. An example where this doesn't work is, I believe it's like a to 1 plus c to 1 plus c. And that is a bad situation. So that kind of type is very complicated, and Yoneda does not apply to it. It is not of this form, because this is not Napierian. This is not representable. This is not of the form of something to see. And so sometimes it doesn't give you a C. And a function something to see always gives you a C. So then it cannot be representable. And so
Basically,
Yoneda is
maybe, right?
It's a maybe, yeah.
Yeah.
And Yoneda is completely powerless for this. But if you had no maybe in there, that is completely fine. That is a Yoneda, pure Yoneda. This is 1 plus a.
I see. Yeah, so the F can be arbitrary, but the C in the left-hand side cannot be. Yeah.
Cannot replace it with something else.
Okay. Okay.
Right.
But X and F are.
Yeah. Right. Anyway,
interesting.
So the answers here, I believe that this is 1 and this is 2.
Yeah, I mean, the intuition on the counter example you gave is that the function on the left-hand side, the X arrow C in the lemma, it has to be a total function, right? And 1 plus C is a way of representing a partial function, where if it's not defined on A, then you map it to 1, otherwise you map it to C. So as long as we have total functions X arrow C, then the Yoneda applies.
Yeah.
Okay, that makes sense. Yeah.
Yeah, that's a good way to put it. So, right, in the going to 1 plus C, like not all of A maps to C. It's like some of them go somewhere else. Yeah.
Right.
Yeah.
Right. Yeah.
Right. So Yoneda is just not applicable. And in fact, this type is quite difficult to describe. So, like for some A's, it's not equivalent to storing a value of A. It's not equivalent to storing a value of 1 plus A. It's kind of more difficult than that. It can store some values and then decide something based on those values. So it's very kind of strange. This type. I was not able to simplify it in any way.
Yeah.
So this is just an example of why
Hmm.
Yoneda can do a lot of simplifications, but not all.
Hmm.
So on that last example, why can't F be 1 plus C? F of
Which
C be
example?
1 plus.
This one?
Oh, yeah.
Oh, that's fine.
No,
Let's go.
that is
Oh,
okay.
that one works. Okay.
Yeah,
Yes.
Got it.
yeah,
All right.
yeah.
Okay.
Right. So F can be arbitrary, but the left-hand side, the X arrow C, the C can't be arbitrary. Yeah.
Right. So you have to put a C there with nothing.
Yeah.
Not a functor applied to C, but just C.
Hmm.
And this is this is also important for other calculations. You cannot use Yoneda unless the first the argument of your function is of this form. And if you have Yoneda for functors, like you need to use Yoneda for functors in the optics, then you need to have a natural transformation. So for all functor, then you have a natural transformation to your functor, and then something. So this must be just your functor with nothing else. With this, so this must be a natural transformation from something into your functor without any changes. And just like here, it must be C without any changes. So if you need to massage your type into this form. And if you can, then you can apply Yoneda. So they have an example here. Right, so you have FA to FB. So this is not directly in the form of Yoneda because it does not have this natural transformation inside. It's an FB with a fixed or FA with fixed types. So you have to first massage it into this form, which you can do in this case. And then you get the result. And this is equivalent to this. Yeah, okay. Anyway.
I thought it was fascinating that this double Yoneda embedding was, discovered or proposed by Milevsky because I think he was, into programming language and types, and not, this generalization was not from any category theorist. So this contribution back to category theory, or from I think programming language theory, I think is great.
Yeah, from the category theory point of view, all we're doing are some exercises with endofunctors and set.
Right.
So, I mean,
kind of boring from a category point of view, huh?
right. I mean, so there are specific endofunctors that are interesting for programmers, and they're interested in their specific properties, like list and maybe and so on. Who cares, right? And then, so here pretty much everything is set category except for C.
Yeah.
Right.
Yeah.
I have to admit that notation, my eyes just kind of glazed over. It's like, oh, I have a category of functors, where the source category is another category of functors, and then we're taking a Hom set, except we're abstracting out the functor part, and what I don't know what all is that.
Yeah, well, this is a translation of this into category language, and I agree that To me, this is also unreadable. I rewrite this in types.
Mhm.
Yeah.
These double line, single line.
Mhm.
I'm lost here. I want my quantifiers. Give me my quantifiers back.
Yeah.
Or else use what? What does Scala do? Is it %1, %2 to
What?
indicate arbitrary arguments?
No,
Uh,
it doesn't. No, Scala doesn't have that.
No, Scala just uses underbar when
Yeah.
you don't care about the. Okay, okay, must be closure then, where you can use
Mhm.
an anonymous function can be where you don't have to do an lambda x. You can just say %1, %2.
yeah.
Right.
Scala does have anonymous functions of one parameter, but can you have more than one? Or you
Yes.
can have more than one,
Yes.
but
Yes.
they have to go in order. You can't reorder.
Yes. Well,
Okay.
Scala has things like this,
Yes,
which is xy going
right.
into x plus y.
So it's positionally sensitive. Yeah.
It's ridiculous. Yeah. I think
Okay.
it's just totally ridiculous. But okay.
Okay. But yeah, you're right. I mean, having this square bracket C set, square bracket set, that is just, it's keeping the type of the following object indicating that, but you're right. The putting the type on the object F itself, I think would have been more
Oh yeah. Oh yeah. I mean,
concise.
the thing is that in this notation, they don't even have F anywhere.
I know.
Right. It's just the minus. It's sort of our
It's
F.
the
And since
the
it
double
appears
minus. Yeah.
Yeah.
Well, is it a double minus or is it a minus? Because anyway.
Right. So the double minus is the inner functor, right? C into set. And then the
Yes.
minus is the higher order functor from C set into set. So, okay.
right. The double minus is the hum functor, I guess. Right.
Mhm.
So
Yes.
Yeah.
So yeah, very hard to read and hard to deal with. So anyway, it's probably they would first write it in Haskell and then we will translate into this.
Yeah.
Yeah, sometimes I found that I would like, oh my God, I can't understand this. And then I'd like write it out in another notation. And then it's like, oh, I could write it like this. Oh, that's what they did. But yeah, it's like sometimes those tricky things you can see as an author of something aren't useful to your reader. Being tricky as a writer of software generally isn't a good idea unless you have really smart readers. And frankly, it's like after I've written it and I come back and look at it later, I'm not a smart reader anymore. It's like, what did I write? Oh my God.
Or maybe just not quite as smart as you used to be.
That could be. Okay.
Yeah, I think that, the problem as programmers we have is that a lot of intuition went into writing the code, but that intuition is left out, right? The code itself doesn't show that progression. And then when you
Right.
read it, you have to recreate that again. And I wish there was a way to, better document code besides just textual comments. But
Yeah, one of the things I found kind of going through some of these examples and trying to do it in like my own language is that often you're like, you're trying to create a function that returns this complicated thing. Well, you take a parameter off of it or something like that, and you're still left with this, Yoneda thing. And I sort of want to be able to say, oh, I still need one of these, or, because you could say as your parameters, oh, my F has this type, but you sort of can't say what I still need is of this type, and so it would be useful, I think, to be able to say that, at least, cleanly. In some languages, like, yeah, you can give a cast or something like that. But it's almost part of the documentation
Right.
to have that information, because you're sort of going through that as you drive the thing. Oh, I need to compute this complex thing. Well, I do part of it, but I still have this complex thing. But if you can't write it down, it's like all in your mind, and it's not clear to the reader what that was.
Right.
I don't know if
Right.
that made any sense, but yeah.
To me, it would be interesting to find out whether the type notation, this kind of notation, or this kind of Haskell-like notation, is actually equivalent to this notation or not. So can you, with maybe different definitions in Haskell, different type classes where functors are not always set to set, but maybe your calculations done in this kind of code-based notation are actually equivalent in power to those calculations. You just need to translate more cleverly so that they're not always just in the functors set to set, but more general functors from C to D. But you still write in this syntax. And then maybe if you show that, then maybe you can stop writing this kind of thing. And you will just write this. It will be readable, and yet you will have full generality. I don't know if that can be done.
I thought the reason why set is introduced, necessarily, is because we are dealing with home sets, right?
Yes.
Now, maybe in an enriched category where home set is no longer a set, but is yet another category of object, then perhaps that's true. I don't know if there is an equivalent Yoneda lemma for arbitrary enriched categories, I presume.
Well, that I don't know.
Yeah.
I think enriched categories are mentioned in the second paper, which it seems unlikely we'll
Okay.
get to.
Yeah.
But I didn't really understand what they were. So that might be a hint.
Yeah, actually, I was wondering if we could spend a few minutes on that other paper, because I just got lost right away, because we have these categories with co-limits and limits, and they're monoidal and they're closed, and what does all that mean? Does anybody have that?
Do you have that paper?
Do I? Well, I know it would be on the
And I could
on the
try to.
website.
Yeah, well, I don't know
Let
if
me
I
see if I
have it in my notebook.
This is the point at which I have to tick off. So are we still
Yeah.
finishing up with what you need to know next week?
No, we're not finished with it.
Yeah, so start with section 4.
Yeah.
And then get to
Did
the other
somebody?
paper.
Okay, yeah, somebody posted it on the chat.
This is it, right?
Right.
Yeah. So
Okay.
just
Well, see you
all right.
next
See
time.
ya.
See you later.
3 weeks
Bye.
from today.
Bye. Thanks.
Bye.
Bye. Where was it? just right at the beginning, this setting, we have a small, complete, co-complete, symmetric, monoidal, closed category. And then this guy's Cosmos. Anybody, I don't know.
I can talk
unpack
about
that.
I can talk about parts of that.
Okay.
So at one point I was working with rings or modules or something in algebra, and I figured out more or less what monoidal categories are. Monoidal category is something that has something like a product. So if you have a category in which binary products exist, and which has a, gosh, what is that? An initial object. So you can take the product of either 2 objects or 0 objects.
Right. Which means you could take as many as you want.
You can, yes. But if you, so that's an example of a monoidal category, but this is the sort of generalization of that. So you have this thing which is written, you know, the X with a little circle, which I read as like tensor product or something like that. So the tensor and the I are the data given for a monoidal category.
Okay.
So that means you can, there's something like a product, and it has something like, and that product has something like an identity, right?
Right.
And exactly what the axioms are for that is not easy to describe. It involves, you know, functors from the product category, and then there have to be natural transformations that make everything work out. Those natural transformations essentially correspond to the laws of a monoid. So for example, taking the product with the identity object should be essentially the same as doing nothing. And the product operation should be essentially associative. But anyway, but just think of it as that little, you know, cross symbol and the I mean roughly that there's a product-like operation and there's an identity for that operation. Does that make sense?
And it's different than composition, right? It's like a whole nother thing added on top of the category.
Yes, it's a structure. It's an extra structure that you're given with the category.
Right.
And it's yeah.
And for these categories, I guess that product is associative. I think there's some where they're not strictly associative. No,
and then there's monoidal stuff. But if it's monoidal, it has to be associative.
Okay.
Or let's see, is that true? I think that may be true only up to isomorphism or something, but it's essentially associative.
Well, that's what I'm saying. Yeah.
Oh, I see.
Like,
yes.
Yeah, strictly monoidal or something like that. You don't need those isomorphisms. It just is associative. If it's not as, if you have to have isomorphisms, then they have, I don't know, lambdas and all.
I got to step away. I'll be right back.
Okay. Yeah, I ran into monoidal categories kind of going through Malutsky's, you know, thing about monads are just, what is it? Monads are more, or something else in the category of monads, or I don't know. Anyway, whatever that saying was, but I forget. But he uses, goes through the monoidal categories to get there. What is a closed category?
I guess closed usually means that when you do an operation, then you get another object within that original set or object or group or something like that.
I think in category closed means that you have exponential objects.
Well, in this case,
I mean, you're right, Young, that closed often means that, but I think they generally, when they're saying you've got an operation, they imply it's implicit that it's closed, right? the whole point of having like a composition operator is that it operates on any two objects and gives you another object. It is
Right.
closed, you know.
Right.
They don't ever say that it's closed, but they mean it, that it's a total. Yeah. And it's injective, whatever.
Right. So I don't know if the closed here means that normal word or if it means something more than that.
Just normally you would say Cartesian closed category for category that has products, co-products, and exponentials.
Mm-hmm.
And so I presume these are the same. So closed means it has exponentials.
Okay.
It has also limits and co-limits,
And
which means it has a product and a co-product as well. But then it has this extra monoidal operation.
Right.
and the symmetric applies to the monoidal, and it means
Yes.
that the
Yes.
Yeah.
maybe you already said this, that the product is there's an isomorphism if you just flip the two sides of the
Mm-hmm.
monoidal operation. Yeah.
Mm-hmm.
Okay. So it's kind of like commutative, but with isomorphism.
Up to isomorphism. Yeah. It's cool.
Yeah.
I don't know about Benabu cosmos though. I guess this is the definition of a Benabu cosmos, huh?
Yes, I think so.
So closed, we think is Cartesian closed,
I
or
was looking it up on.
it has exponentials. Maybe. Yeah.
I'm not sure about that, but okay. I thought it was just closed under that tensor product, but I don't know if it's redundant to say that. If something is
Yeah, that sounds
monoidal.
redundant
monoidal,
to me. I think there must be something more that they mean.
okay.
In Wikipedia, closed category is a category with an internal Hom functor. Let's see. So it's got an internal, you can see this, right?
Yes.
Internal Hom functor. Which shows Yoneda arrows.
So
guess
it's
that's-
internal. What does internal Hom functor mean? Internal means that object, the Hom set is an object of the category itself.
Yeah,
Is that what internal means here?
I think so.
So it's
Yeah, somehow.
okay. Wow.
I could click on that.
That behaves like a Hom functor, yes, but takes values in the category C itself. Okay. Yeah.
This is
But I
for example, if you look at group homomorphisms between commutative groups, abelian groups,
mhm.
those homomorphisms themselves have a natural abelian group structure on them. You can add and subtract them. So that's an example
Okay.
of the,
Right. Okay. That's a pretty strong property then, this internal Hom functor, that it has to, in a sense, behave like set. Okay.
Yeah.
And then the Yoneda arrows. Wow. Oh boy, so many things to learn.
Yeah. Well, this is just Yeah. Natural in B and C and dinatural in A. All right, well.
Yeah, what does dinatural mean? Oh dear.
Well, I know that. Yeah, now that's clear, right?
Oh, okay, dinatural. So it's got the contra on the first argument and covariant on the second.
Yes.
Okay. Okay, so it's these, okay.
There's a hexagonal diagram that needs to commute.
Yeah, because the A there appears both in the covariant position and contravariant position. Okay.
Right, right.
Oh,
Okay, well, hopefully we don't need all that, but I started reading this and got about this far and wasn't sure. And then they
right.
kind of, they start referencing other papers, including the one we were just reading, I guess.
Yep.
Anyway.
Oh dear. And then they also introduced co-end calculus. Oh no.
Right. And
That's
then
one
there are
of my
these, what?
ends and co-ends. I still struggle with the definition of those. So I don't have an understanding of those.
Yeah. They're kind of like sums and products, but other than that, I don't really get it.
Right.
And then you got these L's and R's, which maybe has something to do with the Yoneda arrows. I don't know. Well, we'll just have to unpack this little by little. Category of context. So yeah, so we get down to the optic as being this, you know, end of basically an integral of all this stuff. So yeah.
You see, it says in the second paragraph above, in a closed category, the object of morphisms from one object to another can be seen as lying inside the category. This is the internal home. In other words, a morphism from X to Y is another object in the same category.
Right.
Which means that it's like an exponential object.
Right. Yes.
And so you need the arrow. Just let's rewrite this square brackets BC as just function from B to C.
Yep.
So then it's a function from A to B to A to C.
Right.
That is one instance of Yoneda. You need to do for all A on the right. So that's a Yoneda arrow. The Yoneda arrow is a function that realizes this isomorphism. But if you don't know what these things are, then you cannot write them as arrows. So you have to write them as square brackets. And then you have to postulate that you have this Yoneda arrow. Whereas in the normal case, Yoneda is a lemma which you prove. So these arrows exist. You know how to write them. But in this case, you don't know how to write them because square brackets BC is not the same as an arrow from B to C. It's some object which has some properties and you don't know what those are. So you have to postulate that there are some further arrows that are natural, dinatural, and so on.
The bracket BC is sort of like that's the internal hom, right? So it's
Yeah.
basically
Mhm.
some object within the category representing the functions or
Yeah,
the
but
arrows.
but
from
in
B
what
to
way
C.
does it represent the functions? You don't know that.
Yeah. Right.
Mhm.
But you know it's an object, and so you can create an arrow from it to other things.
Right. But
Ugh,
that's fantastic.
right.
It's very interesting. I would like to prove in the usual case that the Yoneda arrow is dinatural. It's not so obvious. I mean,
Mhm.
anyway, I have worked quite a lot with dinatural transformations, and initially I thought they are great. Now I think they're not so great.
Mm.
And actually,
Because
so initially I thought that dinatural is equivalent to relational parametric, which is not true. And so just like natural transformation is automatic if you have fully parametric code. And dinatural transformations are just what you have to do if you don't have covariance or contravariance. If you have a type parameter which is both in covariant and contravariant positions, and you cannot use naturality, so you use dinaturality. And I thought that's it. That's what you have to use. But actually, it's not enough. So dinaturality works, but in some cases it does not work for some functions. And so now I just think, okay, well, dinatural is a weaker property than what you need. So for example, I was proving properties of fold left, and dinaturality is not enough. Fold left is a function that has a type parameter which is both in covariant and contravariant positions. And so initially I thought dinaturality is all I need to prove properties of it, but that's not true. And so anyway, just
Okay.
just an aside.
Interesting.
All right.
Yeah. Yeah.
Well,
So their category V, it's V, right?
Oh.
A script V, this
Yes.
thing we were looking at in the new
where'd it
profile,
go?
the new lens paper. Yeah.
Yep.
Script B,
Yeah.
this guy.
So they're not very good with examples here, which is bugging me. Should I imagine that V is set? Oh, no, wait, what do they say? Oh, it models the types of a programming language.
Yeah, I didn't
Okay.
get that. And V is enriched over itself. What is that?
I think that's basically,
That's saying that it
That's
has
the
the
closed.
HOM stuff.
That's the
That's right.
closed part. Yes.
That's the home. That's
Oh.
right. That the home object is an object of V itself.
Okay.
So I should
where
imagine,
was
maybe
that?
as an example, I could imagine that V is like the set of Haskell types. Right?
Yes.
Okay.
This is what you're talking about.
Yeah, yeah.
Objects, model types, and the
Or sets,
morphisms.
I guess. You could think of sets because that works fine too.
Mhm.
Uh-huh.
And I
Right.
guess
And morphisms model the programs. And there they're using programs to just mean sort of functions in general, I guess.
Right.
yeah.
But is there a reason why we couldn't just think of V as set? Are there cases where it's no longer a set? I'm just curious. Like in Haskell, is the type system of Haskell beyond set? Cannot be modeled using set? Because you don't have self-application. I mean, that's the one area where lambda calculus takes you outside of set. But if you're staying without self-application because you have a strict stratified types, I'm just wondering where. But anyways, okay.
I'm not sure about that, because there was a paper where John Reynolds says that, types are not sets, and he has a proof about it. And I suspect it relates
But
to the fact that,
okay.
go ahead.
But that's for the polymorphic type lambda calculus, right? So is Haskell a polymorphic in that sense?
Haskell
I'm
has
wondering.
polymorphism, sure. I mean,
Okay.
all over
Yeah.
the place, right?
Okay.
And,
Yeah, you're
and
right.
So if you can have those polymorphic types as, things that you then quantify over, I think maybe that's where you get into trouble eventually,
Okay.
right?
I'm just wondering if in this setting they are assuming that kind of a language, or if they're just assuming a simply typed language without polymorphism. But okay,
Yeah, yeah.
I'm curious.
It may be that that's what this is somehow capturing, that in this setting, you don't get any kind of foundational problems or something like that.
Right.
But maybe we can just think of V as types and morphisms as functions, and see how far we get.
Well, I should go, but
Yeah, me
thanks
too.
for coming. I'll see you in 3 weeks, I hope.
3 weeks, yeah.
Yeah.
All right,
Okay.
everybody.
Thanks.
All right.
Bye-bye.
Bye.
Thanks,
Bye, everyone.
Sergey,
Bye.
for leading
Sure.
us through this.
Very much.
Well, hopefully we can go through this next time.
Okay.
Yeah. Bye.